Let's take a look at the Minimax algorithm. By understanding the algorithm itself better, you will understand the code and what I do in that phase. So the Minimax algorithm is used for games where two players take turns making moves. The board state is always known to both players. It's not like a card game where some cards might be hidden and you might not know who has what. The game ends when one player wins, or sometimes in special cases there might be a tie. Each player will try to develop a strategy that leads to a win. The algorithm depends on an evaluation function. The evaluation function can take a board in any state and give you a relative value so that you know the strength of that particular position. Remember that player 1 wants to maximize their score, while player 2 wants to minimize that player's score. That's why this is called the Minimax algorithm, because one player wants a maximum score and the other player wants to minimize that player's score. So we use a tree to organize the Minimax algorithm. So here's a Minimax tree. At the top, there's a single position. Now suppose from that position there are 3 possible moves. Okay, and you can make any one of those 3 possible moves. For each move that you make, then there are going to be an additional set of possible moves. And if you make any of those, then there's another list of possible moves. And it can go on for quite a while. And for chess, it's been estimated that there are 10 to the 120 possible moves, which, by the way, happens to be a larger number than the known number of atoms in the universe. So what happens is the evaluation function assigns a value to the leaf nodes of the tree. Okay, and I want to point out that you can go as deep as you want. Sometimes you get to terminal leaf, but you can actually adjust the depth of the probing that you take. So here, note that the leaf nodes all have values, and these values represent their relative strength for the player at the top. Note that from the bottom, the max is the next level up. Okay, the maximizer is always going to take the greatest value that it sees and use that because obviously that person wants the maximum value. The minimizer is always going to take the smallest value that they see because they want the smallest value. You'll notice that the maximizer has taken the greatest value. For instance, note that 3 leaves, 23, 28, and 21 are grouped together. Well, the maximizer took 28 from that group because it's the greatest value. And so forth. The same thing holds true for all of these groups of leaf nodes. The maximizer is always going to take the greatest value. Now you're going to guess that the minimizer will take the smallest value. So note here that I have 2 values, 28 and -3, and they're grouped together. The minimizer will take -3. And in the next group, -4 gets pulled up and -73. Because remember, the minimizer wants the smallest value. Now, you will probably predict which one the maximizer is going to take. The maximizer will take -3 since it is the greatest value. And that's exactly what happens. The maximizer will now use the move corresponding to -3. Okay, so let's look at some code. Before we do that, let's run the application. And I'll click on the Start button and watch this play a game of Connect 4 by itself. Okay, and the elapsed time was 9 seconds. And let me show you how the main logic organization goes. First, I need to tell you I have a board class, which encapsulates the Connect 4 board. Then I have a Minimax class, which gets the move, or gets the next move, and it uses the Minimax algorithm. Once you have the move, I do a place piece in the board, and finally I invalidate the dialog window so it redraws. This line actually just toggles between red and yellow players. Let's take a look at the basic Minimax algorithm which we're using to get the next move. It's called do search, and it gets all of the legal moves, and then it loops through those moves, and each one of those moves, by the way, is going to correspond to those nodes that you saw in the Minimax tree. First thing it does, it saves the board, it makes the move, and then it recursively calls do search, and it will continue to make recursive calls to do search until it reaches the depth that it desires. Then once it's back, it compares min and max and keeps track of which is the min and which is the max. And we're only going to set the position, meaning row and column, when we're at depth of 0. By now, you're probably wondering when I'm going to start writing parallel code. The most obvious place to parallelize is in this for loop, which goes through each move. So I can try something like this. And sure enough, that will parallelize the for loop. The problem is that will do it for each level of depth that I go down. These are called plies. So for each ply, it will be parallelizing it. Well, I wrote a blog several weeks back warning against this. You can over parallelize, and that will actually steal performance. What we want to do is keep this limited to the very first level, or depth of 0. Okay, so instead of doing this, I'm going to go ahead and paste in some pre-written code, and then we'll walk through it and take a look at what I've done. First, I'm going to tell OpenMP that I want 4 threads. Okay, and the reason I want 4 threads, and I need to know that I have 4 threads, is because I have to have 4 copies of these values. If I don't have 4 copies of these values, then I will get race conditions and we'll get unknown results. As I go through this, first I get the thread number. It's going to be 0, 1, 2, or 3. This is all the same code I had before, nothing new. But instead of the local min and the local max variables that I was using, I'm going to use those arrays. Now I have 4 of them, 1 for each of the threads. So the code looks the exact same, but I will have an affinity for the min, max, and position. Once I'm done, I will have to combine those myself. Now realize that OpenMP has this notion called a reducer, and that works well for things like multiplication and addition and stuff. But in this case, it doesn't have a mechanism for what we're trying to do. So we have to manually combine it ourselves. So now, with that pasted in, let's go ahead and run it and see what kind of a performance enhancement we get. Press the start button. And we have an elapsed time of 5 seconds. About half of the time of the original run, which didn't use OpenMP. As you can see, it is fairly easy to parallelize the Minimax algorithm using OpenMP in Parallel Studio. It provides significant performance improvements, and it can be applied to other Minimax games such as chess, checkers, and tic-tac-toe.